Welcome back to the deep dive. Today we're plunging into something huge. Psychiatric disorders. I mean, the burden is staggering, immense distress, people unable to function. And it costs the world, what, 5 trillion US dollars? It's mind-boggling.
It really is. And the core frustration, the thing that makes it almost cruel, is the lack of clear, objective ways to diagnose and treat these conditions.
Exactly. You've got this global crisis of the mind, and we're often relying on, well, subjective reports.
Right. The current symptom-based diagnosis, what a patient tells you, it often means treatment gets delayed, or maybe it's not quite the right fit for that person.
Which is why everyone's hunting for biomarkers, isn't it? These objective signs.
Precisely. We desperately need something concrete, measurable, that actually reflects what's happening inside the brain.
So, okay, when we talk about looking inside the brain for these markers, what's the main technology everyone gets excited about? What's its initial appeal?
That would definitely be electroencephalography, EEG. Basically, it's a recording from the scalp, captures the brain's electrical buzz.
The buzz, I like that.
Yeah, it's the sum total of all these tiny electrical potentials from millions of neurons firing, or rather, their postsynaptic potentials. It's like listening to the brain's orchestra from outside the concert hall. Not the individual instruments, but the overall sound.
Listening from the outside. Got it. And the appeal is, well, pretty obvious, right? The sources really hammer this home.
Oh, absolutely. Key advantages, it's non-invasive, no needles, nothing scary.
Huge plex.
It's way cheaper than, say, an MRI. Much more accessible.
Right.
And you get real-time data. It has fantastic temporal resolution, meaning it catches those super fast changes in brain activity, millisecond by millisecond, things slower methods would just completely miss.
So zooming out again, why is finding these biomarkers so absolutely critical for psychiatry? You mentioned the subjective diagnoses.
Well, yeah, the current system, like using the DSM, the Diagnostic and Statistical Manual, it leans so heavily on interviews, on observed symptoms, and that can lead to diagnostic instability.
Meaning the diagnosis can change.
Exactly. Symptoms shift, new ones pop up. It can be a bit of a diagnostic Wild West, honestly, which makes getting the right treatment and getting it quickly really tough.
Definitely paints a picture of the challenge. And that's where EEG comes in with all its promise, looking for those specific characteristics.
Researchers have looked at a whole host of things. For depression, there's been a lot of talk about alpha asymmetry. That's an imbalance in alpha waves between the left and right sides of the brain.
That one's been a bit controversial, though, hasn't it?
It has, yeah. Not always consistent, but they've also looked at increased gamma band power, linked to higher cognitive stuff, and changes in REM sleep, like more REM sleep, but starting sooner. Even things like higher EEG complexity, maybe suggesting the brain's struggling to regulate itself.
Okay. And what about bipolar disorder?
There, the focus has often been on abnormalities in alpha activity too, especially in frontotemporal areas. Seems linked to cognitive issues. And what's really interesting is how some brainwave patterns, beta, delta, theta, might actually normalize when someone responds well to lithium treatment.
Ah, so potentially a way to track treatment.
That's the hope. Could be a way to monitor if it's working. Plus, things like increased beta activity during manic episodes might signal that neural excitation.
And schizophrenia, that seems even more complex.
It is. Sources mention increased delta and theta power but less alpha power, suggests baseline disruptions. But maybe even more revealing is the work on event-related potentials, or ERPs.
ERPs, right? Those tiny signals in response to specific events.
Exactly. Things like P50 sensory gating deficits. Basically, the brain can't filter out irrelevant noise, leading to that feeling of being overwhelmed.
I see.
Or N100 amplitude reduction, suggesting issues processing sounds initially. And the P300 component that reflects attention, memory, decision-making, that's often different too.
These all sound like really hopeful early insights, right? Getting a real glimpse under the hood.
They definitely offer objective windows into what might be going wrong in these incredibly complex conditions.
So if we found a truly reliable EEG biomarker, what's the big aha moment we're hoping for? How would it change things for a patient versus today's system?
The R-naught moment, the real game changer, would be getting to truly personalized medicine in psychiatry. Imagine a quick EEG helping a doctor diagnose depression or bipolar much earlier, maybe telling similar conditions apart.
Okay.
Or even predicting which medication or therapy might actually work best for you, for that specific individual.
So less trial and error.
Way less trial and error, faster effective treatment, better outcomes, less suffering. It could really shift psychiatry from that diagnostic Wild West to something much more precise, much more data-driven.
That's a powerful vision. Okay, but here's where it gets really interesting and maybe a bit darkly funny. Despite all that promise, EEG biomarkers aren't really standard clinic tools yet for diagnosis. Why not?
Yeah, this is the reality check. There are some major hurdles. One big one is spatial resolution. It's just low.
Meaning,
Remember the orchestra analogy. Listening from outside the hall, you can hear the music, but pinpointing exactly which violin in which section, very hard. EEG struggles to tell you precisely where in the brain activity is coming from, especially deeper down.
okay, so location is fuzzy. What else?
Then there's the noise problem, and this is where it gets almost comical. EEG signals are so easily messed up.
By what?
Oh, everything. External stuff like electrical interference from equipment nearby, sure, but also your own body.
My body.
Yeah, blinking your eyes, clenching your jaw slightly, tiny muscle movements in your scalp, even your heartbeat showing up in the signal. The skull and scalp themselves resist the electrical signals. It's like your body is actively trying to sabotage the recording.
Haha, okay, that is kind of darkly funny. Your own body is noise.
It makes getting a clean signal, especially for the really subtle brain patterns linked to psychiatric conditions, incredibly difficult. Those faint whispers are easily drowned out by biological static.
It sounds like a nightmare just trying to get usable data. How on earth do they manage that?
Oh, it's a constant battle. Technologists are incredibly vigilant. They meticulously prep the scalp. They watch the patient like a hawk for any movement. They use sophisticated algorithms to try and filter out heartbeat artifacts, eye blinks.
Wow.
It's this continuous detective work trying to isolate the real brain signal from all that physiological and environmental clutter.
And I guess interpreting that messy data isn't simple either. It's not just looking at squiggly lines.
Not at all. You need serious signal processing know-how, deep knowledge of neurophysiology, bioinformatics skills. You have to know what's signal, what's artifact, what's just noise.
Right. And you mentioned consistency earlier, or lack thereof.
Ah, yes, the standardization issue. Or maybe the non-standardization issue. It sometimes feels like a totally novel concept in parts of the field.
Meaning,
Different labs, different clinics, they might use different equipment, different procedures for recording the data, different software, different algorithms for analysis.
so everyone's speaking a slightly different language.
Kind of. It leads to results that are inconsistent. You can't easily compare study A to study B, and that really, really hinders progress towards something reliable enough for widespread clinical use.
That makes total sense. And layered on top of all that technical stuff is the nature of the disorders themselves, right?
Exactly. Psychiatric disorders are messy. Their heterogeneous depression looks different in different people. Symptoms overlap massively between disorders. People often have more than one condition, high comorbidity.
So unlike, say, Huntington's, where there's a clear genetic marker.
Right. There's rarely a single biological smoking gun for something like schizophrenia or major depression. The DSM symptom clusters, while useful clinically, actually make finding a clean, consistent biomarker even harder for researchers. Diagnostic instability can even mess up the research studies themselves.
Which I suppose brings us perfectly to maybe the most, let's say, illustrative example of the pitfalls, the split alpha incident.
Oh, yes. The split alpha scandal, a classic.
So some researchers announced they'd found this new phenomenon, right? 2 or more peaks close together in the alpha frequency band. Sounded pretty groundbreaking.
Looked like they'd found maybe new brain generators working at slightly different alpha speeds. Very exciting stuff. But the punchline, delivered quite bluntly in one of our sources, is that split alpha isn't physiological at all. It's not real.
Not real?
Nope, it's a completely spurious effect, a ghost in the machine, an artifact caused by messing up the math.
Lexing up the math club.
By using a standard tool, the fast Fourier transform, or FFT, on data segments that were too short. When you analyze a wave using too short a snapshot, you can get this thing called spectrum leakage.
Spectrum leakage.
Imagine trying to identify a musical note by hearing just a tiny fraction of a second of it. The analysis might mistakenly create echoes or phantom frequencies around the real note because the window was too small. That's basically what happened. These split peaks were illusions created by the analysis method, not by the brain.
Wow. So they found a glitch and called it a discovery. That's quite something.
And it gets worse. They started assigning meaning to these phantom peaks, claiming they represented new generators in different parts of the brain.
Oh dear.
And then the real kicker, suggesting that where these supposed generators were located depended on which reference electrode they used for the recording.
Wait, isn't that like Electrophysiology 101? The reference is just a comparison point. It can't change where the signal comes from.
Exactly. It's a fundamental misunderstanding. It was, frankly, an embarrassing blunder, but a really instructive one.
Absolutely. It just hammers home that fancy tech isn't enough. You need rigorous methodology, which ironically brings us to the other side of EEG, the clinical side, where they live by these incredibly strict rules.
It highlights the unsung heroes, the EEG technologists, and their rulebook, these minimum standards.
And the standards themselves sound intense. One source quotes the American Clinical Neurophysiology Society saying minimum standards provide barely adequate fulfillment of responsibilities to the patient. Barely adequate.
That tells you how high the stakes are, how precise you need to be.
And the details. Minimum 16 channels recording at once, specific electrode types like silver chloride, checking impedance, the electrical contact, making sure it's super low, ideally under 5K ohms.
Right, because even a little bit of bad contact acts like static, drowning out those faint brain signals we need. And using that precise 10-20 system map for placing all 21 electrodes, ensuring everyone measures from the same spots.
It's incredibly meticulous. And then there's filtering the signal. You mentioned that can cause problems too.
Oh yeah, filtering is essential to reduce noise, but it's another potential minefield. Pausal filters, the ones you can use live, can actually distort the timing, create ripples, shift when activity appears to happen.
So it looks like something happened later or earlier than it really did.
Potentially, yes. Zero-phase filters are better for preserving the signal's shape and timing because they process forwards and backwards, but you can only use them after the recording is done.
Okay.
So the technologist has to be constantly watching, spotting potential filter artifacts. Even the common 60 hertz knot filter for a power line interference is used sparingly because it can mess with real brain activity near that frequency.
It's just layer upon layer of potential issues, and then they deliberately try to provoke brain activity, the choreography.
Standard procedures, simple stuff like opening and closing the eyes, watching how alpha waves change.
Okay.
But then it gets more intense, hyperventilation, having the patient breathe deep and fast for at least 3 minutes.
Why?
It changes brain chemistry slightly and can actually provoke seizures, which helps in diagnosis, both epileptic ones and sometimes psychogenic non-epileptic seizures too. Though obviously they don't do it if someone's had a recent stroke or is pregnant, safety first.
Still sounds pretty intense. What else?
Photic stimulation, flashing lights at different frequencies, another classic seizure provocation technique.
A party trick indeed.
And then there's sleep. The guidelines want a good chunk of sleep recording, maybe 30 minutes plus 20 minutes awake, often induced by partial sleep deprivation beforehand.
Which you mentioned there were no safety studies for.
Correct. One of those slightly dark, ironic footnotes in the guidelines. Or sometimes they use melatonin. It's quite an ordeal for the patient, all to get reliable data.
It really underscores the human element. The technologist isn't just hooking things up. They're managing the patient, noting every little thing, even testing responsiveness during a potential seizure.
Absolutely. Calmly asking, lift both arms up or repeat these words, horse, table, while someone might be having a seizure. It's incredibly skilled, high-stakes work.
So given all this complexity, all these challenges, where do we go from here? Is AI the savior?
Well, that's certainly the big hope. Artificial intelligence, deep learning. The promise is that these techniques could revolutionize EEG analysis. Handle the toys, the complexity, maybe spot subtle patterns humans miss, automate artifact rejection, analyze huge data sets.
Find those elusive biomarkers.
That's the goal. Overcome many of those traditional limitations.
There's always a but, isn't there?
Always. AI needs massive amounts of really good, well-characterized data to learn effectively. Huge data sets, meticulously cleaned and labeled. That's a challenge in itself. And then there's the interpretability problem. These AI models can be like black boxes. They might find a pattern, but can we understand why it's relevant?
So are we just trading one kind of messiness for another? Could AI just find new, fancier ways to generate split alpha artifacts only faster?
Haha, that's the cynical but not entirely unfair question. It's possible. AI is a powerful tool, absolutely. But the core need for scientific rigor, for critical thinking about the data and the methods, like the split alpha story showed us, that doesn't go away. If anything, it becomes even more important.
So bringing it all together then, what does this mean for you, our listener, trying to get your head around this? EEG clearly has huge potential. Non-invasive, fast, relatively cheap.
And it has given us real promising clues about the brain mechanisms in depression, bipolar, schizophrenia. It hints at that future of objective diagnosis and personalized treatment.
But that journey to the clinic is just riddled with obstacles. Technical complexity, noise, standardization issues, human challenges, and these really basic methodological traps like split alpha.
Right. It shows that cool tech isn't the whole story. The underlying science, the careful interpretation, that's crucial. Split alpha isn't just a funny anecdote, it's a really stark warning about how easily we can fool ourselves, especially when we're desperate for answers. Rigor matters. Understanding your tools matters.
So for you listening, understanding these challenges is key. It's a reminder that even in hard science, maybe especially in hard science, critical thinking about how we get our data is just as vital as the data itself. And it shows the reality of scientific progress. It's often messy, painstaking, rarely a straight line.
Especially when we're dealing with the brain, it's also that cautionary tale. Beware of new phenomena that might just be glitches in how you looked. Always question the methods.
Which leaves us with a final thought. In a world crying out for objective answers to very real subjective suffering, what does it truly mean when even our most sophisticated scientific tools require such intense scrutiny to tell a real insight from, well, a glorified glitch? Maybe the hardest part about understanding the brain isn't just its complexity, but our own struggle to read its signals without accidentally making things up along the way.